Hello, in this video I'm going to talk about dark matter. So this is the matter that our theories and observations of the universe tell us is out there and in large quantities, but we can't see it. We don't know what it is, and in a lot of cases we don't know where it is, and that's why we refer to it as dark matter. And dark matter really got into vogue in the 1980s and 90s, where people were speculating about what it could be, where it could be. All these different theories were flying around. It's been slightly overshadowed in the last couple of decades since dark energy turned up on the scene. But both dark matter and dark energy are still very much active areas of research. These are crucially important to our understanding of the universe. Yeah, we want to pin down what these things are. So, is there something new out there? Is this dark matter actually there, as all our theories are telling us? Or have we got some theories wrong? Or is it a bit of both? I mean, this is what we need to figure out. So that's why it's such an active area of research. Now, before I get into what people think dark matter might actually be, let's do a little bit of the history of this. So we're going back to the 1930s and looking at rotation curves of galaxies. So I mentioned this in my previous video on galaxies, but let's do a quick recap. Rotation curves, this is where we're looking at objects at various distances from the center of a galaxy, plotting out their rotational speeds, and then you get a curve, a rotation curve. Now, the predictions back in the 1930s, which had, the sort of ideas people were looking at were sort of Kepler's law ideas. It's not exactly like Kepler's laws, but the idea that we get looking at the solar system of how objects are moving around, that as you get further away from the sun, the objects are moving more slowly. And we see this in Kepler's third law and in Kepler's second law. Look at those areas that are being swept out. As you get closer to the sun, you're moving faster compared to further away in these elliptical orbits. We've got Kepler's third law with the relationship between orbital period and distance. So they were looking at these sort of things, plus some variations based on the distributions of matter that were actually evident, the matter they could see in these spiral galaxies that they were looking at. And what would we expect? And the prediction was a curve that would look something like this. So you've got a drop off in the rotational velocities with distance once you've got past a sort of certain period, certain distance close to the center of the galaxy. So this was the prediction. The observations, as I spoke about before, don't look like that at all. They end up having something like this. So actually, as you move further out, the rotational speeds are staying fairly flat. If anything, they're increasing. And we're getting these massive differences between the old predictions and then the observations. So these predictions based on the visible distribution of matter. So conclusion off of this, and this was really cemented by the 1970s, is this is strong evidence for dark matter, for matter being in a sort of spherical halo going around the spiral galaxy much further out. And that was then allowing people to build models that would match the observations. So this was really kicking dark matter right into the foreground of observation of astronomical research. Of course, this was going alongside developing theories of the Big Bang model, and you had different versions of the Big Bang model that were matching up to different ideas about dark matter. Is it hot dark matter? Is it cold dark matter? These were the terms that were getting thrown around, depending on the descriptions of how people were thinking galaxies and stars and such like were forming. Did you have things like neutrinos, high energy, low mass particles, or did you have stuff that was a bit more sluggish but substantial? So you had these different ideas that were being thrown around. The 80s and 90s were a hotbed of all of this, and then dark energy turned up in the late 90s, and things all started changing again. So the models, though, predict that we've got around about 5 times the amount of dark matter, slightly more than 5 times dark matter to ordinary matter in inverted commas. So the stuff we can see. So we've got 5 times as much matter that we can't see as the stuff that we can see. This is then, you take all of the dark matter and the visible matter, you then double that up, and then That's the dark energy part of it. So if you were going to split up what we currently think the universe to be, then you're looking at a sort of, I don't know, 5 to 25 to 70, that sort of thing, in terms of visible matter to dark energy. These are all, rough numbers. I've rounded them all to the nearest 5. But this is what our current models are telling us. So there's a lot out there. We got 95% of the universe we're not really that great at explaining. So what could this stuff be? What is it? Why is it dark? Now, it could be dark for a couple of different reasons. It could be dark because it's ordinary stuff that we're familiar with. We just can't actually see it. So, is it planets? Is it brown dwarfs? Is it neutron stars? This is all stuff. It's all baryonic matter. This is all quark matter. It's all our 3 quarks. We're not having to dream up new types of particles and extend our particle physics and the standard model and everything. So is that what it is? It just happens to be in places where we can't see it. It's not really interacting with much. It's just hard to detect. And one of the candidates that got kicked around in that was the people were very pleased with the name that they came up with, MACHOs, massive compact halo objects. So you can see the halo coming in, this spherical halo around these galaxies. Are there a lot of massive? So we're not talking about things like neutrinos. We're talking about, they don't have to be huge, but massive in terms of baryonic to a large extent. Okay, it might aggregate up to things like planets, neutron stars, or brown dwarfs or whatever, but massive, compact. So yeah, not big clouds of gas and things, but they're compact objects. So yeah, maybe they are brown dwarfs, and they're going around in this halo. So we had that kicking around. They're hard to detect because if it's a brown dwarf, well, it's not. There's no nuclear fusion going on. It's not. We're not looking at a star there. Same with neutron stars. They're quite hard to pick up on quite often, and you can observe them indirectly if they get in the way of other objects. And because of that, observations are suggesting there's not enough of these things. There aren't enough other objects. There isn't enough visible matter which is getting affected by these machos if they were around. You'd expect them to be getting in the way of a lot of things at a certain frequency, and we're just not seeing this. So machos don't seem to be enough. What if it was going to be non-baryonic matter? I mean, it could be new particles. It could be particles that we know about. There was quite a while people were looking at neutrinos. Okay, we know about neutrinos, but they're not baryonic. Do they have mass? Do they have enough? If because there's a lot of them around, we know how many neutrinos can get produced in stars and supernovae and other events. There's lots of them about. So that was an area that people were looking at for quite a while. So is it non-baryonic matter that we know about, or is it new stuff? Maybe there are new particles that we don't know about. But then if we've got new particles that we don't know about and they're interacting in different ways and they're not to do with neutrinos, so neutrinos, this is our weak nuclear force. If they're not to do with electromagnetic, then they're not emitting photons. Then what are they? Do we need a new force? I mean, is this, we've got a whole new interaction that we're getting into here, and we're really expanding the standard model. We're coming up with a new gauge boson and such like, and having all of that. But all of these fell under the again, they were really pleased with themselves when they came up with WIMPs to go alongside machos. So weakly interacting massive particles. So let's take the example of a neutrino. At least we know what they are. So if a neutrino had mass, so that gives us the M. So massive as in not a photon. They've actually got some mass. So if neutrinos have mass, well, they are weakly interacting. We know that much. So maybe there was enough of them. Maybe there's other ones, as I say. So they had this lovely combination of terms, machos and WIMPs. Now, we haven't really got to the bottom of any of this. People started moving on to other ideas as well. primordial black holes. These have been thrown around. So primordial, early universe. Maybe in the early universe, lots of black holes were being formed. Maybe more than we actually see around and think would be formed now. We don't know about a lot of processes in the early universe. It's theoretical, it's speculative. But then, it's got the plus side that we know that black holes exist and they can have a lot of mass. But there's a downside of, well, how does this fit in with our Big Bang models? How does it fit in with our cosmological models? How would these form in the early universe? How would they affect cosmological models? How would they affect everything else? So there's a lot of questions about primordial black holes, whether that would be sufficient. And then people come up with other options as well, which although probably wouldn't explain everything in themselves, like none of these things do. Maybe it's a combination of all of these things, or maybe there's something new, who knows? People then say, well, what if there's something wrong with the theories that we've got? Maybe general relativity isn't exactly as we think it is on the galactic or greater scale. When we get on to beyond galactic scales, maybe there are things we don't know about relativity. Maybe that would be something that will get refined. And that might explain some of the issues, but it doesn't look like that would explain everything, because we've still got stuff like these rotation curves that seem to be well within our descriptions. And there's some in there that needs to be found. So it could be that we come up with something new that will explain everything. It could be a combination of a whole lot of stuff. But there's something going on, and people haven't got to the bottom of it, and it's still being researched. So it's a really exciting area of astronomy, astrophysics, and all of that. Same with dark energy. Dark energy discoveries are coming up continually on the news. There was another one only last week about how all of the things that people thought they knew about dark energy were being questioned again. It seemed to be different to what people have been thinking for the last 10, 15, 20 years. So you're getting these developments happening all the time. This is a really fast-paced, fast-moving field. So, it's exciting times for astrophysicists. But from the dark matter point of view, we've still got these big questions. They're sitting there. What is this stuff? Where is it? Okay, we've got some ideas with these halos around galaxies of where it is, but where else might it be? What else might it be? So if you want a career in astrophysics, this might be your baby in the future. Nobel Prizes to be had in this area, that's for sure. So there you go, dark matter.